Okay, so good afternoon, everyone. So welcome to the first lesson on chapter 14, metals. So as I explained to those in the Zoom room earlier before recording started, I think metals is a very long and important topic. Okay, metals are important in our lives. Most elements, if you look at the periodic table, are metals. But beyond that, most students also don't realize that it's a very important topic to study before the O levels. All right. It's a very commonly overlooked topic. So I certainly hope that you will give time to really understand metals well. All right. Now, the first set of notes is basically on metallic bonding, which you had learned way earlier in term 2. So the first set of notes is just a recap, which we will do now. Okay, so metals, let's start. Now, obviously, the bonding within metals is called metallic bonding. We already know this. Metallic bonding involves positive metal cations. So your positive metal ions surrounded by a sea of delocalized electrons. So I think we can remind ourselves, why do metals have delocalized electrons? Where did these electrons even come from? Now, these electrons are the valence electrons of metals. So in metals, their valence electrons can be easily delocalized such that they are no longer fixed onto any atom. They can move freely throughout the lattice. All right. So if you look at the structure below, there are two boxes. Obviously, you have to fill in the boxes, right? Now, this is actually an O-level question. They got the pure chem students to fill in the two boxes. Quite clearly, the plus over there refers to the positive metal ions. And the rest, the smaller particles, are your sea of delocalized electrons. Okay? Now, this explains to you why metals are good conductors of electricity. Because they have electrons that are delocalized. Delocalized means the electrons can move freely. Therefore, they conduct electricity. Okay? So this is the structure, the giant metallic lattice, which you have learned under metallic bonding. So what are the physical properties of metals? I think this is not new to you. Firstly, metals have high densities and high melting and boiling points. All right. So this is true for most metals except for group 1 and mercury. So for your group 1 metals, okay, like sodium, potassium, these group 1 metals are the exceptions to this. They have relatively low melting points, relatively low densities. Okay, so you must remember this. The exceptions must be remembered. Okay, next. The next property is about conducting electricity. This one, let's add in for clarity. All metals, including group 1, all metals are good conductors of electricity and heat. All right. Let's add in the all. Okay. There are no exceptions to this. Now, why is that so? Now, we have since learned that conducting electricity means you must have free moving ions or electrons, right? So in the case of a metal, what is moving? The delocalized electrons. The ions don't move. What happens is the electrons are the ones that are free to move. This is commonly tested in MCQ. They like to test you this. The positive metal ions, they are in fixed positions. But it's the delocalized electrons that are free to move. All right. So you must know this. It's the delocalized electrons that move, not the ions. Okay. Now, besides that, you have also learned physics so far. Good, right? Physics and chem links together. You have learned under thermal physics that conduction is a way of transferring thermal energy. How does conduction work? Conduction works when particles collide, and through the collision, they transfer thermal energy onto the next particle. All right. So obviously, if the electrons are free to move, they can collide frequently, and the frequent collisions between the electrons allows thermal energy to be transferred. Okay. Now, so this is where Mr. So will start linking to physics, okay? Since I have time. Now, I hope you have realized by now, okay, fast thermal transfer, okay, means it's a good conductor of heat. All right. But I'm not sure if you have thought about it. Something that is a good conductor of heat, will it heat up fast or slow? Good conductor of heat, does it heat up fast or slow? Let's ask someone. Okay, Audrey, if it's a good conductor of heat like a metal, will it heat up fast or slow?
It should be fast, right?
Fast lah, okay? So since primary school, you all learn, right? How come your pots and pans, the base must be made of metal? Because metals are good conductors of heat, so they heat up more quickly, right? That's the reason why pots and pans are made of metals, because they are good conductors of heat and they heat up fast. Right? I'm not sure if you realize also that they require less heat energy to increase the temperature by 1 degree Celsius. Because metals already have delocalized electrons in them, they actually require less heat energy to increase their temperature by 1 degree Celsius. That's why they heat up fast, right? They become hot. The temperature increases really quickly. Then you look at the phrase I've written, heat energy to increase temperature by 1 degree Celsius. Does it sound familiar to one of those physics definitions you have learned under thermophysics? Have you learned any definition that sounds like that? The amount of heat energy needed to increase the temperature of 1 kilogram of the substance by 1 degree Celsius. Have you learned that before? Does it sound familiar? Should I ask someone? Okay, maybe ask someone first, okay. Jing Kang, does this definition sound familiar? From physics, not chem, physics.
Specific latent heat of fusion.
Okay, that one is specific is correct, but latent heat of fusion is about melting, okay? But specific is correct. Not specific latent heat of fusion, but specific heat capacity, okay? So if you recall, the definition of specific heat capacity is the amount of heat energy or thermal energy needed to increase the temperature of 1 kilograms of a substance by 1 degree Celsius. So if it requires less heat energy, the specific heat capacity is low. And that's why if you notice, your notes must have given you the specific heat capacities of different things. Metals generally have lower specific heat capacities compared to other substances. Okay. So one of the substances that has very high specific heat capacity is water. Water actually has quite a high specific heat capacity. Okay. Okay, I sidetracked a little bit, but I hope you realize that, okay, this is related to the properties and bonding within metals. It's related to the fact that metals have free moving delocalized electrons, which allows it to transfer thermal energy really quickly. Therefore, it's a good conductor of heat, and hence that explains why the specific heat capacity of a metal is usually lower than other substances. All right. Okay, can I move on? Give me a thumbs up if I can move on. Okay, let's move on. All right. Okay. Now the next page again is not new. You have seen wires. Copper metal is used in electrical wiring. Okay, copper metal is a very good conductor of electricity. Okay. Now there are other metals which are also very good conductors like gold. Now gold is actually a even better conductor of electricity compared to copper. So gold is even better a conductor. But why do you not use gold in regular wires at home? I think the answer is obvious, right? Gold metal is rare. It's expensive. You should not be using it to make wires at home. Having said that, because gold is such a good conductor of electricity, okay, we use it in chips, microchips that are found in your iPads, laptops. So iPads and laptops typically contain a little bit of gold. And that's also the reason why when your laptop is spoiled, not you able to use it anymore, you should send it in for recycling because the recycling company can extract the gold from the laptop and of course recycle it. Okay. Now, besides that, we also said this before, pure metals are malleable and ductile. So this one, we mentioned it before. I hope you remember. Malleable starts with M. So the idea is it can be molded into different shapes without breaking. Okay, so it can be molded into different shapes. Now, what does it mean by different shapes? What shapes are there anyway, right? Well, metals come in different shapes. Okay, you have seen that aluminium comes in a foil, but you can also buy aluminium as a powder. Okay, similarly, iron. If you were to buy iron, you can buy iron as a bar, a rod, a sheet. So these are different shapes, basically. Okay, now ductile. Ductile means it can be stretched or pulled into thin wires without breaking. Okay, so it has to do with pulling. So quite clearly again, pure metals are ductile. You can pull them into the thin wires without breaking. And what's the reason for this? How come the metals can be so easily deformed or molded into different shapes? It's because the atoms are of the same size in a pure metal. Pure metal is an element. If it's an element, the atoms are all the same size, right? So pure metals are elements. So the atoms are of the same size. It is the same type of atom. So if it's the same size, it will be arranged in an orderly manner or a regular manner in layers. So when you are in layers, it's very easy to deform it because when you apply a force, the layers of metal atoms can slide over one another easily. This sliding action allows it to change its shape easily. When a force is applied, that is, all right? So this is about pure metals. Now, is this always desirable? It depends. If you are trying to mold it into different shapes, this is desirable. But obviously, this also means that you wouldn't use pure metals when you want it to withstand forces. For example, if you wanted to make pillars in a building, your pillars in a building cannot be pure metals because the sheer weight of the building will deform the metal easily. Can you imagine if your building deforms? That could be very dangerous, okay, for the integrity of the building. So very often we don't use pure metals, we use alloys, and I'm sure you already know that. Okay, alloys are mixtures of a metal. There must be at least one metal element with one or more other elements. Now this one can be metal or non-metal, okay? So the other element in an alloy mixture can be either metal or non-metal, no restrictions. Now these are the common alloys, bronze, brass, so on. Okay, bronze. Bronze is copper and tin. Brass is copper and zinc. Solder is tin and lead. Pewter is more complicated. Pewter is tin, copper, antimony, and bismuth. All right. Now, the first four are bronze, copper, and tin. Okay. So what do we use bronze for? Well, very commonly, we use bronze to make ornaments. We use bronze to make medals. So bronze medals, right? So they contain copper and tin mixed together. Next, brass. Brass will be familiar to most people in band because virtually all the band instruments are made from brass alloy, copper and zinc. All right. Solder. Solder is tin and lead. Solder is commonly used in your microchips because that's how we try to use some alloys to make the microchips a bit stronger. Pewter. Now, pewter is one of those things that had many things mixed together. Now, basically, the added elements in pewter allows it to be more shiny, looks better. So pewter is commonly used in ornaments as well. All right. Now, move on to the last two. The last two, steel. Steel, you must remember, okay, iron and carbon. All right. So you can see what I meant. Alloys need not be metals. In steel, you only have iron metal plus carbon mixed with it. Carbon is a non-metal. All right. Then you have stainless steel. Stainless steel contains iron, carbon, chromium. All right. Chromium is an important element and also nickel. Okay. Now, are you expected to remember all this? No, but you should remember some common ones. What are the common ones? I would recommend remembering at least these, these 4 start ones. All right. Now, would alloys have a fixed melting and boiling point? I think we have done this before, so I shall not bore you. Now, alloys are mixtures, okay? They are mixtures. Mixtures are by definition impure. So now you have your answer, right? Alloys are impure. So alloys do not have a fixed melting and boiling point. Because they are mixtures and are impure. Okay, so the idea is you need to mention and understand that mixtures are impure. Okay, so this one I think is not new. We have done this before. So why do we use alloys? Well, there are many reasons. The first important reason is that alloys are harder and stronger than the pure metal. All right, just now we mentioned pure metals are so malleable, you can deform or mold them so easily. Alloys are much harder and much stronger. That's the main reason why we use alloys. Next, alloys can be used to improve the appearance, make it more shiny. Alloys can also make it more resistant to corrosion, more resistant to rusting. Okay, and finally, in some cases, you want the alloys to have a lower melting point than the pure metal. Okay, but that's a less common reason. Okay, the most common reasons are the first 3 reasons listed there. So you need to know how to explain that alloys are harder and stronger. This one, I think we can do this. So first, from the diagram of the atoms, you can clearly see already. Because it's a mixture of different elements, right? There's a metal and another element. So because it's a mixture, the atoms will be of different sizes naturally. So when it's of different sizes, it will break up or disrupt the regular layered arrangement of atoms. Okay, you can see here, there's no more regular layers. So when a force is applied, the layers cannot slide over one another easily. And hence, it's just harder and stronger, okay? Okay, the final part, which is also from our notes previously, which is steels and their users. Steels with a plural, okay? Okay, Audrey, sorry.
Joe, can alloys be compounds?
No, alloys are not compounds. Alloys are mixtures, okay? So Audrey has a good question. So alloys are mixtures. You mix them, you do not chemically combine them, okay? Which also means, leads us to the next point, right? Why are there steels? It's not just one steel, right? There are steels. That means there are different types. How come there? Because it's a mixture. It's not chemically combined. So you don't have a fixed ratio of iron and the other element. It's not a fixed ratio. So you can generate different types of steels depending on how much carbon you have. Because there's no fixed ratio, okay, and the elements are not chemically combined. So the different types of steels, you can see there's mild steel. Mild steel contains low carbon, meaning less carbon. High carbon steel, more carbon. So you can see, this illustrates to you there's really no fixed ratio, right? You can have low carbon, high carbon, all right? You could even add other elements like chromium in, that makes it stainless steel, okay? Now, chromium is important because chromium is the element that actually makes it resistant to rusting, okay? So we will look at this later on in metals part 4, exactly how to prevent rusting. And using alloys of iron, like stainless steel, using the alloy, like stainless steel, is a way to prevent rusting. But how? Okay, so we'll learn that in part 4 of metals. Okay, now do you have to remember the 4 types of steel? The answer is yes. Okay, this is one of those learning outcomes that are tested under pure chem. Okay, so you need to know, importantly, that low carbon steel is strong and malleable. But the moment you have a lot of carbon, once you have high carbon inside the alloy, it becomes brittle. Brittle means it breaks easily. So like knives. Knives made of high carbon steel, they are strong. But the moment you twist it, you manage to twist it a little bit, it will just shatter. That's what it means by brittle. Okay? Can? So you do need to know the 4 types of steel, what are they used for, and what are their properties. Okay? So up to this stage, it's just a recap of what we have gone through in term 2. Okay? So now what is the main objective of this chapter moving forward? Well, we have just seen the physical properties. Physical properties are like melting point, density, electrical conductivity, thermal conductivity. These are physical properties. We have seen the mixtures, which are called alloys. Again, alloys, they don't have chemically combined together. Alloys, you just physically mix them together in no fixed ratio. And that's why alloys can be separated into the elements using physical methods. Okay? But that's not it, right? This is chemistry. We should learn the chemical properties. Chemical properties always means chemical reactions. What kind of reactions do metals undergo? Okay, so that's the next part. Okay. Now you can see every set of notes has an introduction, more or less. You just want to read it and gain an interest in how chemistry can be around you, right? So if you look at the short introduction I have, I'm sure you have heard in human history, we have a relatively long history. Okay, we have ancient civilizations, old societies, okay, in the past called the Bronze Age, the Iron Age. Wow, sounds familiar already, right? Iron, bronze. Bronze is an alloy. Okay, bronze is an alloy of copper and tin. Okay, but to have a whole period of human history named after the metal, that means the metal was of central importance to their lives. For example, Iron Age was like so important. It's so important because iron metal was discovered. They could extract iron and they could use the iron metal to make swords, axes. They could use it for cutting, farming. So can you imagine how revolutionary that was? When you can farm, you no longer need to go around and hunt. You can lay down your roots, settle in one place, start farming, start getting your food from near your house. And that led to the birth of towns and cities as we know it. Wow, sounds so awesome, right? But this Iron Age was in 1200 BCE. In 1200 BCE, It's not 1,200 years ago. It's 1,200 plus 2022. So it's about 3,000 plus years ago. Iron was discovered 3,000 years ago. Wow. But some metals, like potassium was discovered very recently, quite recently. Potassium was discovered in 1807. So you can see potassium was discovered about 200 years ago, whereas iron was discovered 3,000 years ago. So why is it that they're so different? How come you don't have a potassium age, the sodium age in ancient history? Well, that probably has to do with something that's different between them. Maybe iron and potassium are just different. But how are they different? Maybe in terms of their reactions. So let's see. All right. By the way, if you think this introduction was nonsense or like unimportant, you are wrong. This actually came up before for combined science. They actually asked the students, explain why certain metals were discovered very late, like potassium, whereas some other metals like copper were discovered a long time ago. They actually asked the students this. So when I tell you such things, right, it's for you to go and find out and Google and wonder. Okay? So I hope you are wondering about this along the way. All right? Now, obviously, this leads us to the important concept. Potassium and iron are different because potassium just reacts differently. Potassium is just very, very reactive. Iron, not so. Less reactive compared to potassium. So metals have different reactivities. Some are very reactive, some totally unreactive. So we can order them into a reactivity series. Importantly, the reactivity series of metals puts the most reactive on top. Top is the most reactive, bottom least reactive. All right, so these are the metals you need to know. Potassium on top, then sodium, calcium, magnesium, aluminum, carbon. We have inserted carbon for a reason later. Zinc, iron, lead, hydrogen, copper, silver. So you need to remember this series. All right, you have to remember this series. So how do you remember this series in this order? Well, we have an acronym, right? So the acronym starts with the first letter of the name. Please send cats, monkeys, and cute zebras in large heated cages soon. So potassium, sodium, calcium, magnesium, aluminium, carbon, zinc, iron, lead, hydrogen, copper, silver. All right. How long will it take for you to learn this reactivity series of metals in this way? Well, it depends. If you stare at it frequently, you will remember it better. All right. So like even right now, I can easily recite, please send cats, monkeys, and cute zebras in large heated cages soon. So I can recite it easily. All right. So it's something that comes with practice. But more importantly, we need to talk about how to use the reactivity series, okay? Memorizing it is just one thing, using it is another. So if you were to compare, let's say, sodium with iron, what can you say? Sodium, because it's above iron, equals is more reactive than iron. Okay, because it's above iron, sodium is more reactive. So the converse is true, right? Iron is below sodium, so it's less reactive than sodium, which I am sure you have learned by now. Sodium, super reactive, okay? Iron, not so. Okay? So this is how you use the reactivity series. Depending on whether it's above or below, you can work out which one is more reactive. On top is more reactive, below, less reactive. Okay? Now you must be wondering, why did we even put carbon and hydrogen in? Carbon and hydrogen are non-metals, okay? They are not metals. That's why I highlight in yellow, I put a star next to it. It's because they are non-metals, but I still put them in the series. Why? For these reasons, all right? Carbon is a non-metal, but we put it in because in the next part of this chapter, we will see that elements above carbon cannot be extracted by reducing the metal oxide with carbon. Wow, you can see redox, reduction. Okay. So let's try to process this. Element above carbon. Okay, let's look at the series. What's above carbon? Let's read. Above carbon, potassium, sodium, calcium, magnesium, aluminium. Right? These are above carbon. If it's above carbon, are these elements reactive or unreactive? Let's ask someone. Tiha, the metals above carbon, are they reactive metals or are they unreactive metals?
Reactive.
Reactive, right? Potassium, boom. Sodium, boom. Reactive. So basically, elements above carbon means reactive metals. Okay? I hope you realize by now, reactive metals cannot be extracted by reducing their oxide with carbon. Cannot. Okay, so what are the reactive metals here? Potassium, sodium, calcium, magnesium, aluminium. Okay, then we have hydrogen, also put in the reactivity series. For what? Hydrogen non-metal. It's a non-metal, hydrogen non-metal. How does it work? Why do we put it in? Because metals above hydrogen can react with acids. Metals below hydrogen cannot react with acids. Oh my God. Oh, wow. Finally. Now you know why certain things like copper cannot react with HCl. Because copper metal is below hydrogen in the reactivity series. So it cannot react with acids. Okay? So this is the reason why we put carbon and hydrogen into the reactivity series to enable us to work out, number one, can it be reduced by carbon? Number two, can it react with acids? Okay. So with that, I think it's okay. I will move on. Okay, so now we are going to be learning a series of reactions. Okay, each of it may look like a bunch of facts, a bunch of descriptions and equations to learn. And that's why today I don't want to do all of them. Okay, I just want to go slow, do each of them slowly. Okay, so at the end of today, you may realize that, oh, actually I didn't learn a lot of reactions, but that's fine. I want us to focus on every single reaction and really understanding it. Okay, so let's go for deep understanding today as opposed to how many things you have learned today. So let's start. Now, the first reaction is that some metals, not all, some metals react with cold water. Okay, now when they react with cold water, they form the metal hydroxide. Can we please highlight the word hydroxide? So they form the metal hydroxide and hydrogen. Hydrogen obviously is H2. Let's remind ourselves. All right. Now, as mentioned just now, not all metals react with cold water. Not all. In fact, only the top four. So let's circle. Only the top four metals, the four most reactive metals, react with cold water. This means they are very reactive metals, okay? So if it reacts with cold water, it's reactive metal. It must be, okay? So let's fill in the blanks now, one by one. Okay, let's go slowly through the list. Now, as we go through the list, you will see there are bullet points, right? Do we need to remember these bullet points and be able to describe them? Well, the answer is actually yes. You may be asked to describe the reaction of sodium with water. That means you need to give the bullet points. Now, is it really so hard to remember? Not really. Okay, so let's go one by one, starting from the most reactive, potassium. Now, potassium floats on water and it reacts very violently. with cold water to form potassium hydroxide. Why potassium hydroxide? Because we know that it forms the metal hydroxide. So in this case, potassium hydroxide. Okay, so what's the equation? Let's write it out. Okay, so let's write it out. So potassium plus water gives you KOH, potassium hydroxide, and H2 gas. Okay, to balance is 2, 2, 2, 1. Right, 2K plus 2H2O plus forms 2KOH plus H2. Okay, I've put in the state symbols as well. Okay, so that you are clear. Now this reaction, okay, you've seen before. When I taught you all group 1, I've shown your potassium metal drop into water, right? It immediately catches fire. All right, it immediately catches fire. Okay, the moment it hits water. That's how reactive and how hot the whole piece of metal is. So the heat energy produced causes the hydrogen gas to catch fire and explode. All right. So when you do potassium with water, it's very important to add only a very small piece of the metal. You add a large piece of metal, the whole container will just explode in front of your face because it's that reactive. All right. Ken? So the first 2 bullet points are really not difficult. It's really just describing the reaction, how reactive it is, how violent it is, and what is formed. Potassium hydroxide and hydrogen. Now, potassium hydroxide solution is alkaline. This is important. You need to know this, right? Hydroxide. Hydroxide is alkaline. It will turn red litmus paper blue. Alkaline, right? Red litmus paper turns blue. But the difficulty is universal indicator. So this one you got to remember. Universal indicator is not just blue. Okay, alkaline, there's blue, there's purple. So potassium hydroxide turns universal indicator purple or violet. Why? Because potassium hydroxide is a strong alkali. The pH is about 14. Okay, so that's potassium reacting with water. Okay, so that's the most reactive, potassium. Now we move on to sodium. Now sodium is below potassium. So you can already deduce sodium below potassium in the reactivity series. So sodium is less reactive. If it's less reactive, obviously, the reaction is not very violent. It's just violent. So you can see basically the difference is I've dropped the word very. Potassium is very violently. Sodium is violently. So sodium floats and reacts violently with water to form sodium hydroxide. So remember, it's always the hydroxide when you use water. So the equation, 2Na plus 2H2O forms 2NaOH plus H2. Okay. So again, the hydrogen gas is produced. Hydrogen gas produced may catch fire and explode also. But you see the word may, may means not necessarily so, right? Not 100% confirmed. So it really depends how much sodium you add. But for potassium, it confirmed will catch fire. Okay, so similarly, sodium hydroxide. Sodium hydroxide, you've used it so many times. Acids and bases, QA, you've used sodium hydroxide so many times. Sodium hydroxide is an alkaline, obviously, right? It turns red litmus paper blue. And similarly, universal indicator turns purple or violet. Okay, so NaOH, definitely purple or violet. Okay. Okay, the first two, potassium and sodium, group 1 metals. Are we okay? If you're okay, give me a thumbs up so that I know that they are okay and I can continue. If you have questions, also ask at this point. Okay, so let's move on. Okay, now we will move on to the next one. So calcium is below sodium. So you can imagine in the reactivity series, potassium and sodium are right at the top, group 1. Then you have calcium, magnesium, group 2. So your group 2 metals are less reactive than group 1 metals. Okay, so calcium is less reactive than sodium because it's below sodium in the reactivity series. So it cannot be violently anymore, right? It cannot be reacts violently. So what is after violently? Oh, very violently, then what's next? It's called readily. So calcium reacts readily with cold water to form what? So again, you can predict it's called calcium hydroxide. Okay, it's a metal hydroxide and hydrogen. Okay, so how do you balance the equation? Okay, so this is the equation. All right, you can see that the balancing is different because obviously calcium is group 2. Group 2 will form Ca2 plus. So the formula of calcium hydroxide is Ca bracket OH bracket 2. Okay, it's important. That's why the balancing is different between sodium and calcium. Okay, so this is calcium hydroxide and hydrogen. Now, calcium hydroxide obviously is alkaline as well, so it will turn red litmus paper blue. But the difference now is that it turns universal indicator blue as well. Now, what's the reason for this? The reason for this is because calcium hydroxide is a weak alkali. The pH is around 10 to 11, and that's the reason why your universal indicator doesn't go to purple, it goes to blue only. Okay. Okay, so we went from very violently, now readily. Okay, so what's next? What's after readily then? Okay, what's after readily is obviously magnesium, right? Magnesium is less reactive than calcium, all right? So it cannot be reacting readily anymore. Now, we say that magnesium reacts slowly or better, very slowly. How slow is slow? You need a few days for magnesium to react with water. So it reacts very slowly with cold water. And what this forms is magnesium hydroxide. Obviously, same reaction, right? The hydroxide is formed. But let's add this in front of magnesium hydroxide, which is solid magnesium hydroxide. The magnesium hydroxide is formed as a solid precipitate. Okay? So the equation, how do you write it? So again, magnesium solid, magnesium metal is a solid, plus water, forms magnesium hydroxide. But this time around, it's not aqueous, it's solid. Okay? So how come magnesium hydroxide is a solid? Well, if it's a solid precipitate means it's insoluble in water. Okay? Because magnesium hydroxide is insoluble in water, it will be formed as a solid PPT. Okay, it's white in color. And you can see the reaction is so slow. In order to have enough hydrogen gas to fill the test tube, you really need a few days. So that's how slow the reaction of magnesium plus water is. Okay. All right. So once you're done, can I have a thumbs up so I know that you're done? Okay. Now I'm just going to zoom out. Stay on the same page, but I'm going to zoom out, okay? So going back to what we said, metal plus cold water gives you the metal hydroxide plus hydrogen gas, okay? So how cold is cold? Some of you will be wondering, right? Does it mean that if I use tap water, it's not cold? Okay, so cold water literally means water that hasn't been heated up. So if you use room temperature water, that's considered cold water. All right. So if in the exam they write metal plus water, it means metal plus room temperature water, which will be this reaction. All right. So cold water refers to room temperature water, all right, or colder. Now, we also talked about magnesium. Magnesium reacts very slowly with water, right? Very slowly. So does it mean that magnesium is an unreactive metal? Do you think just because it reacts very slowly with water, it's unreactive? Does it make magnesium unreactive? That's my question. Okay, so let's ask someone. Estella, magnesium reacts very slowly with water. So is it unreactive?
No.
No, right? Look at the whole grand scheme of things. There are so many metals in the reactivity series. Only the top 4 most reactive react with water, you know? So even though it reacts slowly, it must still be one of the top 4, right? So really, magnesium is still a reactive metal, just that it's not as reactive as, say, potassium. All right? Magnesium is still a reactive metal because it can react with water. The other metals can't even react. Okay? So that's metal plus water. I'm just going to do one more, which is the next one, metal plus steam, and we will stop there. Okay? Now, the next page, metal plus steam. But isn't steam just water? We get steam when we boil water, right? So steam is just water, but in the gaseous state. So what's such a big deal about this? Well, to boil water, you must heat up the water to what temperature, people? Okay, let's ask someone. Rishi, to boil water, I need to heat the water up to what temperature?
100 degrees Celsius.
Yeah. So to have steam, don't you agree it needs to be 100 degrees or more? So I'm sure you agree with me now, it's hot. Just now was room temperature cold water. Now you're talking about high temperature. Okay? So that is the difference. That temperature makes all the difference that you're going to see next. So now you look at it, metal plus steam. There's going to be a major difference. It forms the metal oxide. Please highlight this. Metal plus steam gives you the oxide. If you compare with just now, if you use water, it gives you the hydroxide. Okay, so water gives you the hydroxide, OH. Steam gives you the oxide. Okay, and it also forms hydrogen gas. So that is the difference. The difference is that the product is not the same. Next, because it's hot, high temperature, steam is hot, high temperature results in an overall much faster reaction. Because when it's hot, you have learned in physics, when things have high temperature, hot, it means that the particles have more kinetic energy. When the particles have more kinetic energy, they are able to react much more quickly, which is to say, now your series of metals, more of them can react with steam. The first 4 can react, but now, because it's hot, particles have more kinetic energy, more can react. Okay? So everything until iron will be able to react with steam. Because it's hot, particles have more kinetic energy, therefore they move faster, they collide more frequently, therefore more of them can react. So you compare this with just now, water only the first 4 can react, right? Top 4. This one, wow, all the way until iron can. All right. And because it's hot, every single reaction here now will appear faster, will appear more violent than before. So just now, like magnesium reacts very slowly with water. But the moment you change to steam, the drama changes. Because magnesium is now exposed to high temperature steam, magnesium will now react violently with steam. And this produces not the hydroxide anymore, steam. Steam produces magnesium oxide and hydrogen. So the equation is Mg plus H2O gas, cause it's steam, forms magnesium oxide, which is a solid, and hydrogen gas. All right. So steam is a gas. Okay, it's very important to realize this. Okay, just give me a minute. Okay, I think my screen. Okay. Okay, hopefully you can see it soon. Yep. Okay, so this is the reaction. Now, magnesium is quite interesting. Magnesium, when it reacts with steam, doesn't just form the magnesium oxide. It actually gives you a very nice, brilliant, or dazzling white glow. So magnesium is commonly used in fireworks because it's very bright when it reacts. Okay? So if magnesium is already violent, can you imagine potassium and sodium? Wow, it won't just be violent, right? Potassium and sodium with steam, explosive. So we will not add potassium and sodium to steam, explosive, unsafe to carry out. Okay, next, we move on to zinc. So just now we say, right, very violent, violent. What's after violent? So zinc, after violent should be what word? Hot zinc reacts. How? Jia Bao? Okay, so very violent, and what?
Can you repeat your question?
So hot zinc reacts how? How should I fill in the blanks? So just now we learned the most reactive is very violent. Then after that, violent. After violent, what is it?
Oh, readily.
Yay. Okay.
Okay.
So I'm teaching you all how to remember. So you all must remember how to describe this, because that could be the essay question. So hot zinc reacts readily with steam to form zinc oxide. Okay. So the equation is not difficult to write. I'm sure you can write it in the flash. Okay, so it's easy. Okay. Now, zinc oxide is special. You have learned the color of zinc oxide. So I hope you remember. Zinc oxide, solid, okay, is yellow when hot. But when you cool it down, it turns to white. Okay, so this is a very unique color of zinc oxide, which you should learn. Yellow when hot and white when cold. All right. So we go down to the next metal, iron, right? Now, iron, okay, is interesting, okay, because it's less reactive than zinc. So in order for it to react with steam, you need to make it red hot. Red hot means very hot. You need to heat it up to a temperature whereby it starts glowing red. If it starts glowing red, it's hot, like really hot. All right. So it tells you that you need to heat iron up to a reasonably high temperature for it to react. Okay, so red hot iron reacts. How? How does it react? So we go through the hierarchy again. Very violently, violently, readily. What's next will be slowly. So red hot iron reacts slowly with steam to form. Now this is an interesting compound. It's called iron tetroxide. Okay, so very shortly, I'll show you what this means. Okay, so a few things are, there's a reversible arrow here. Second thing, the steam again, H2O gas. So this is an interesting compound because you have never encountered this before. Right? What is Fe3O4? Fe3O4 is iron tetroxide, which you have not seen before. Now, what iron tetroxide actually is that it contains actually two things. Iron 2 oxide and iron 3 oxide. Okay. So iron tetroxide contains iron 2 oxide and iron 3 oxide. And that's why you see when you add up the chemical formula is Fe3, because it's 1 iron plus 2 iron, Fe3, O4, 1 oxygen plus 3 oxygens. All right. And you can see that this reaction is reversible. This immediately tells you that, oh, this reaction is actually quite slow. It's so slow to the point by which it doesn't give you a lot of product and it can be easily reversed. It tells you that iron is probably not very reactive as compared to zinc or magnesium. All right, iron is less reactive. Okay, and you have to heat up the iron constantly in order for the reaction to continue. If you stop heating, iron actually stops reacting as well. So again, another sign to you that iron is less reactive than zinc or magnesium, which makes sense, right? Iron is below zinc and magnesium in the reactivity series. Okay, so the one with iron is a bit more peculiar, more unique, so you got to learn it. All right. Now, these can also be found in your textbook, of course. So I've given you the page numbers, page 252. That is the corresponding page in your textbook, which you can also refer to get these equations again. All right. Now, obviously, the obvious elephant in the room. I have done magnesium, I have done zinc, I've done iron. But clearly, I have skipped aluminium, right? I've skipped aluminium in the process. Why? Why did I skip aluminium? Now, aluminium is a very interesting metal, in my opinion. Aluminium, if you look at its position, it's actually above zinc and above iron, which means that aluminium is actually more reactive than zinc and iron, right? So aluminium is a reactive metal, okay? But yet we use aluminium so often at home, right? Aluminium is used as aluminium foil, which is used to wrap your food up, right? And you think about it, that's strange leh. Aluminium is used to wrap food up. And then sometimes after wrapping the food, right, we actually send it into the oven to bake, for example. Surely the oven is very hot. So why doesn't the aluminum foil react at such a high temperature? We say the steam. Why doesn't the aluminum foil react with oxygen in the air at such high temperatures? So that is the question that we will attempt to answer the next time. All right. So the next time we meet, we will first start discussing and revising this, of course, but I want to discuss the unique chemistry behind aluminium. Aluminium is supposed to be quite reactive, but yet it seems like we can safely use it at home, even in the oven, without worrying that it will burn, it will react with the steam. But why? Why does aluminium seem so safe to use, even though it's quite reactive? All right. So next time we will continue with the rest of this. So today, what did we learn? We have learned the physical properties of metals and alloys, important. Secondly, we have also learned the reactivity series of metals and the fact that you must memorize the series in that order. Thirdly, we have learned two reactions, the reaction of the metal with water and the reaction of the metal with steam. It's different. It gives you different products and different metals can react. So obviously for water, only the top four most reactive metals will react, namely potassium, sodium, calcium, magnesium. Whereas for steam, more metals can react all the way to iron. All the metals until iron can react. And the reason is because steam is high temperature, which allows the particles to have more energy to react. Okay, so that's the two things we have learned today. The next lesson, which is Monday, I believe. Okay, I'll confirm again. We will continue with the rest of this chapter. All right, so I shall stop the recording here. Thank you.